In this video, we evaluate this definite integral. We've got a rational function and we're asked to find that net area under the curve from x equals 0 to x equals 2. And this is problem 53 from section 15 or section 5.2 of the Larson Calculus book, 10th edition. That section is about antidifferentiation and integration involving the natural logarithmic function. So these integrals all tend to involve this basic rule that the antiderivative of 1 over x is the natural log of the absolute value of x plus c. But frequently we have to use u-substitution first. So we look at this and we look at the integrand and we say, do I have a basic rule for that? No, I don't. Then I'm looking for an inside function. Since there are no obvious inside functions, there are no parentheses, there are no roots, there are no exponential functions with functions inside or trig functions with functions inside. If in that case, when I have a rational function, usually my u, or a good choice for u to start, is that denominator. So we'll let u equal x plus 1. And we'll say, well, then what is du? Well, du is the derivative of x plus 1, which is 1, times dx. So this is our u, and this is du. So I can rewrite this entire integral in terms of u, provided that I can write that x squared minus 2 in terms of u. Well, that's relatively easy to do. All you have to do is solve this for x. And by subtracting 1 from both sides, we have x is equal to u minus 1. Then x squared would be u minus 1 squared. And x squared minus 2 is u minus 1 squared minus 2. And if you want, before we simplify, before we write that integral in terms of u, we can simplify this. This is u minus 1 times u minus 1. And if we distribute, we have u times u is u squared. Outer times outer is negative u. Inner times inner is another negative u. So we're going to have negative 2u. Last times last is positive 1. And then we're subtracting that 2. So our numerator is actually u squared minus 2u minus 1 in terms of u. And we're dividing all of that by u. Okay, well, do I have a basic rule for that? Well, not yet. But when that 1u in the denominator, we can separate the numerator and then we'll be able to evaluate it. So we'll replace that x squared minus 2 with whatever it is in terms of u, which was this u squared minus 2u minus 1. And then the dx is the same as du because our u is just x plus 1. And then u is that denominator. So we've written our integrand in terms of u. We've written our dx in terms of u. But we also need new bounds. To find the new bounds, these are we want to go from one u value to another u value, as opposed to going from one x value to another x value. We substitute the bounds for x into that function u. So u was x plus 1. So I want to evaluate that at the upper bound and lower bound for x. So at x equals 2, we see u is x plus 1. So u is going to equal 3. That's our new upper bound. And at x equals 0, u is 0 plus 1, which is 1. That's our new lower bound. So we're going to integrate from 1 to 3 rather than integrating from 0 to 1 or 0 to 2. Because these are x values where we start and where we stop, and these are u values where we start and where we stop. Now our integral is written entirely in terms of u, and we say, do I have a rule for that? No, but if I just divide each of these by u, then I should have a basic rule for everything. So we'll be integrating from 1 to 3. U squared divided by u is u. Negative 2u divided by u, the u's reduce, and we just have a negative 2. And then negative 1 over u, we've got a basic rule for. So now we'll apply our basic rules. This first one, we use the power rule. Add 1 to the exponent. So we'll get a u squared. And then divide by the new exponent. Dividing by 2 is the same as multiplying by 1/2. The antiderivative of a constant with respect to u is that constant times your variable, which is u. And then we subtract the antiderivative of 1 over u, which is natural log of the absolute value of u. And then we evaluate this from u equals 1 to u equals 3. That means we substitute in 3, we substitute in 1, and then we subtract by the fundamental theorem of calculus. The 1/2 of 3 squared minus 2 times 3 minus natural log of the absolute value of 3 minus 1/2 of 1 squared minus 2 times 1 minus natural log of the absolute value of 1. Natural log of 1 is 0, so that's 0. And this ends up being 9/2 minus 6 minus natural log of 3. And then if we distribute this negative here and here, we have minus 1/2. And then we're subtracting a -2, so that's going to be adding 2. So then I have 9/2 minus 1/2, that's 8/2. So that's going to give us a 4. 4 plus 2 minus 6 minus natural log of 3. The 4 plus 2 minus 6 is 0, so we just end up with a negative natural log of 3. And I'm not sure what that is numerically, but that's the value of our integral. Say, okay, well, what does that look like? How can we visualize that? Well, we can graph that function on the interval from 0 to 2, see if that function is either above or below the x-axis on that interval. Since our final answer is a negative value, I bet there's some of that, or there are some x values on that interval where this function is negative. And the area between the function and the x-axis that is below the x-axis is going to be greater than the area that's above the x-axis. So that when we subtract that area above minus the area below, we get a negative number. That net area is this negative natural log of 3. So let's look at that on Desmos.com. We'll start with the original function. When x equals 0, we see that the y value is -2, right? And then when x equals 2, what is our y value? We get 2 squared minus 2 divided by 2 plus 2. So we get 2 in the numerator divided by 3. We get 2/3. And I don't know exactly what the function looks like as we go from -2, x equals 0, y equals -2 to x equals 2, y equals 2/3. But we know we're going to pass through the y-axis at some point. For some reason, I'm thinking it looks kind of like this. If that's what our function looks like on that interval, this integral from 0 to 2 of the original integrand is this area. Well, actually, it's this area above the x-axis minus this area below. And that turns out to be a negative natural log of 3. And it looks like that it intersects at 1, but that's probably incorrect. So let's look at the graph. So this is our graph. It's a rational function. It has a slant asymptote. I believe that slant asymptote is y equals x. But that slant asymptote isn't of interest to us. We're just interested in the interval from 0 to 2. So let's focus on that interval. And that's what we see. At 0, our function value is -2. At x equals 2, our function value is 2/3. That's what we see. And this area minus this area is negative natural log of 3, according to our calculations. Let's look at a numerical approximation of that. We see that we get the same answer that they do. Now, if we wanted to, we could find that 0 of the function. We'd say that our function is actually equal to 0 when x equals positive square root of 2. Because that numerator would be 0 when x equals square root of 2. So if we evaluate that at square root of 2, if we evaluate the function at square root of 2, this is what we get. We see that 0 there. So this should actually be the sum of 2 integrals. Should be the sum of the integral from 0 to square root of 2. Plus the integral from square root of 2 to 2 of the original integrand. We see that we get the same answer if we add them. Let's look at them separately. This integral from square root of 2 to 2 gives us that 0.19697 approximately. So that area is about 0.2. And then this area between the x-axis and the function on the interval from x equals 0 to x equals square root of 2 is about the 1.3. We take this 0.2 and we subtract the 1.3, and it would get about negative 1.1 as our value, or the exact value is negative natural log of 3. So that's visually what's happening. Now the claim is that we can write this integral entirely in terms of a new variable u. We let u equal x plus 1, and then we got this integral. If u equals x plus 1, we had a u squared minus 2u minus 1 in the numerator, all divided by u. And we were integrating from u equals 1 to u equals 3. We see we get the same value for the integral, so we still get that negative natural log of 3 as our answer. But we can represent that visually in a slightly different way. So rather than graphing f of x, we could graph this function of u instead. So let's graph that. I'm just going to call this g of u. So we've got that as our function now. And now we're integrating this function on the interval from 1 to 3. So we're interested in having the y values between 0, that's the x-axis, and g on the interval from x equals 1 to x equals 3. And we're also interested in the area between g of x and the x-axis. So where the y values, where that g of x is below the x-axis. So we've got that area and that area. Looks very similar actually to the original function, right? It's like we shifted everything over a unit, right? When we do that, this area I think is still that 0.3, and this area, or 0.2, and this area is still that 1.3. So we take 0.2 and subtract the 1.3, we get that negative 1.1 approximately. And we can show that if we want to. So we're going to integrate from 1 plus the square root of 2, or 1 to 1 plus the square root of 2. And then integrate from 1 plus the square root of 2 to 3. And if we add those two together, then we get the original value, the value of the original integral. All right, so that's it. That u-substitution didn't do much because when we replace u with x plus 1, it just shifts the graph 1 unit to the right. But it does allow us to apply our basic anti-differentiation rules to find the antiderivative, which is what we wanted to do.